Alright, so after knowing an isotropic material and knowing its stress-strain relationship, okay, in terms of a 3D, we will now talk about something that is in terms of a 2D, which is a thin plate using a plane stress condition. Alright, same thing, you can go to this channel, my channel, and then you click created playlist. Alright, once you enter, you will come to this thing and search for Sem 3 Mechanics 4N, click it, and you'll come to here. Then next, Control F, and then find your shear, plane stress. Alright, so over here you'll get to know the plane stress assumption, where we will talk about it now. Alright, if you don't know anything, you just click back here. Alright, otherwise we will continue in terms of a plane stress understanding, and we will start now. So the plane stress assumption, after knowing that, is that we cancel all the tree. Something that is related to tree, we will cancel it off. Okay, so you have see there is this tree, we cancel, this tree we cancel, tree cancel, then cancel. So what we left is only this portion and the last row. Okay, so if I were to just bring them all off, alright, give me a while. Yeah, I'll cancel this, I'll bring this upwards. This implies that all these 3 rows will be eliminated. Alright, and I'll bring this here. Over here I'll be removing them because all the trees are gone. Alright, so we will have this thing. If I were to go in over here and put things in a more neater way, this will be your so-called reduced plane stress assumption. So it's a reduced stress state. Okay, it's a plane stress assumption. Alright, so you assume that this 3D cube becomes a 2D thin plate, which is what we're gonna talk about it now. And if you were to compare this matrix to the one that we have just derived, it is exactly the same thing. Okay, this is the one that we have derived, this is the one that is provided. Okay, next, in order to express things in a more easier way, alright, easier way or simple way, alright, we sub in 1 over E minus 1 over E everything as S11, S12, S22 and something like that. Okay, this is why is because if you think about it, in the previous video we talked about S, alright, the compliance is actually called SIJKL. Alright, so therefore there's a meaning in there. So this is why we sub in this 1 over E as your compliance. Alright, so these are all your compliances. Alright, then and over here this whole paragraph, what it means tells you that, okay, you have this particular cube, okay, and you have a certain thin plate, alright, that is in this direction, okay, that is in this direction, and you will have another thin plate, maybe perhaps in this direction, for example. Okay, so there is a 3 layers of plate in this case, as you can see. Alright, so what they're trying to say is that using a plane stress assumption, the meaning is that you assume that you are only talking about this particular blue color one. You are only looking at this particular piece, okay, and the particular stress. This one direction stress is, we call it the unidirectional. Alright, so there is only one direction being put in this direction. Okay, so in this case, we're only looking at this piece of blue color. Alright, not the whole cube itself already. Okay, therefore they are only looking at the piece of it, and this is what it's trying to say all along. Okay, the sentence over here, we expect to load a laminar only in plane stress. This is a laminar, this blue color is a laminar, the purple color one is another laminar. Alright, then this orange color one, the bottom one, is another laminar. So each of the laminar has its own capability to carry different plane stresses. Alright, so the blue color one can carry its own plane stress, the purple one can carry its own plane stress, maybe in this direction, maybe the orange one can be carried in this angle direction, things like that. Alright, so this is what it's trying to say. But this whole example is only talking about a unidirectional thin plate. Alright, unidirectional thin plate, meaning you are only in this direction. or maybe in another direction, maybe something like that. Alright, but what if you're talking about a isotropic material? Alright, so isotropic is most probably will be a somewhat a short random oriented laminate. Alright, so over here these are all your fibers, all very short. Alright, and therefore if you were to make them into a piece of laminate or a thin plate, alright, they are somewhat isotropic. Alright, no matter what you pull, they are strong in all directions. That is what it's trying to say. Okay, and therefore we have come to the isotropic laminate. Our objective over here, isotropic laminate. Alright, and therefore for the isotropic laminate, alright, if I were to let you see that it is in terms of a stress, alright, times Young modulus times strain. Okay, so if you were to compare this thing that I took out from here, alright, because this is actually the same as this, just that we sub in this one as S11, we sub in this one as S12, etc. Okay, but it's the same thing. But over here it's slightly different. Alright, you're actually inverting. Alright, you're inverting the equations, alright, in terms of a stress. Over here is strain. Alright, and in this case this is actually the compliance, while over here this is most probably the stiffness matrix as it says. Alright, so this thing over here is the stiffness matrix, this thing over here is your compliance. Okay, now I'm going into details on how do I derive this thing into here, because I also don't know how to derive, but you just need to know that you switch this, you invert this thing into this form. That's all it is trying to say. Okay, and now if I were to crop this, alright, since we know this comes from where already, I'm gonna crop this over here. Same thing, okay, we're gonna sub in each of them, alright, as in this case is we call it the Q11. Alright, this is the reduced stiffness matrix, Qij. Previously we're talking about is a S, alright, in terms of a compliance. Now we talk about Q in terms of the stiffness matrix. Alright, same thing over here, we write as Q12, etc. I'm not going to go into details. But what you need to know is that your Q is all these equations. Alright, this is only Poisson ratio square. To a more detailed one, if you were to take a look, this is actually Poisson ratio 1:2 times Poisson ratio 2:1. Over here is also the same thing. Alright, so you need to know these things, alright, for an isotropic material. Isotropic thin laminate. Alright, so this is not a material anymore, this is just a thin laminate. Previously in the previous video, I think, alright, in let me say in V5.4, we're actually talking about an isotropic 3D material. Okay, now we're going to talk about 2D laminate. That's all it is. Alright, and the same thing applies if you want to find your Poisson ratio, or you want to find your Young modulus, or your Young modulus and your shear modulus is G is your shear modulus. If you want to know their equations, you can just head back to the isotropic area. Alright, where is it? Yeah, this is your shear system, your shear modulus, your Young modulus. Most probably you'll be given, or otherwise you need to derive the relationships, alright, with regards to all this. Okay, these are all your Poisson ratios, V12, V21, or you can derive from here. Alright, I'll not go into details because I've explained in previous parts. Alright, but you can go to lecture note part 1, alright, page 56, or otherwise you can go to V2.9, alright, in our playlist, alright, and you'll get to see the major and minor Poisson ratio, and the explanations over there will guide you through. Alright, and therefore it's for the isotropic laminate, and please do not be confused with an isotropic material. Isotropic laminate is a 2D, material is a 3D. Okay, and the isotropic 2D is talking about a randomly aligned short material, or in other words, this is a plate, right? 2D ma. Alright, you have all your fibers randomly aligned and these fibers are short. Alright, because you can't have a long random like this. You can't have fibers merge like that, right? No weird, right? I don't know, maybe have, I don't know, but at least you get to know the different stuff already. And therefore, last but not least, alright, we are going to talk about the angle. Previously is isotropic laminate. Now we're going to talk about angle orientated laminate. It's a 2D also, alright, but it's an angle with certain angle. Alright, and I shall see you there.